I'm Rebecca Jiang, and in this paper, we propose an approach for parallel jaw gripper and grasp co-optimization for sets of planar objects. The performance of a gripper is a matter of both its morphology and how it is used. Many works design grippers without optimizing for an intended task, and many other works optimize how to best contact objects. But gripper shape and gripper object contact are rarely reasoned about together. As a result, these optimized grasps are only realized by dexterous manipulators, which incur substantial mechanical and control complexity. Given a set of polygonal objects, an accompanying number of contact points, and their assignments to object faces and gripper jaws, we optimize a parallel jaw gripper that can stably grasp each object. This problem is challenging due to its large and complex design space. In addition to optimizing over gripper position and orientation and gripper shape, we simultaneously need to optimize contact locations along edges and consider compatibility of these decisions across the different object grasps, as well as the stability of these grasps. In this presentation, I'll describe how we pose the co-optimization of grippers and grasps as a tractable nonlinear program. The solution is constrained to stably grasp each object and achieve these grasps without geometrically conflicting with any object. In doing so, we formulate the design problem with a shape parameterization expressive enough to allow the emergence of useful design features while remaining tractable. We leverage the key insight that for a candidate assignment to gripper pose and contact location variables, which we'll refer to as configuration variables, we can represent the objects and contact points in frames fixed to the left and right gripper surfaces, which facilitates posing constraints. Consider this example input information. Here we see the objects and contacts in the gripper frames for a bad assignment to gripper pose and contact location variables. In these frames, the jaws close along the horizontal axis. Note how the contacts are vertically misaligned on the M. The squeezing action of the jaws along the horizontal axis would cause a net torque, preventing static equilibrium. The letter T faces contacted are nearly parallel to the horizontal jaw axis, poorly situated to transmit normal forces to preload the grasp. Contact points on the I lie inside the M and T objects. The gripper would have to penetrate the M and T in order to meet these contacts. In contrast, here's a good candidate assignment to the configuration variables. Contacts oppose each other and contact normals are aligned with the jaw axis. All contacts lie outside other objects. And here's the corresponding gripper. Let's formalize these assessments via convex optimization. For fixed candidate assignment to configuration variables, which we'll call X, evaluating grasp stability via a convex program is well studied. We can also pose shape design as a convex program. We use a piecewise polynomial parameterization and enforce contact and non-penetration. Considering grasp stability and gripper shape, whose variables we'll call Y, takes the form of a convex quadratic program over Y, where the parameter matrices are functions of the configuration variables X. But we're not done yet because we still want to optimize over the configuration variables. The naive formulation is intractable. The problem is non-convex over the joint design space and has a large number of variables and constraints, in particular due to the large size of the shape parameterization. An augmented Lagrangian formulation allows us to solve the convex subproblems over Y alone. We can write down the augmented Lagrangian L as a sum of the original cost and a term that enforces feasibility when L is minimized. What we want at each iteration is to minimize L over X and Y. This is still non-convex and has many variables. But note that minimizing L over X and Y is equivalent to minimizing over X, the min over Y of L. Minimizing over X is optimizing gripper pose and contact locations, which is still non-convex but has few variables. Minimizing over Y is evaluating grasp stability and gripper shape, which is convex. The problem is large, but can be solved globally and efficiently. Here's an animation, again visualized in the gripper frames, of the optimization process iterating through candidate solutions. We share the results for grasping sets of polygons, the MIT letters, and commonly used tools, validating that the framework can be applied to complex objects. We also perform a hardware demonstration of the tool grasps. In summary, our method optimizes grippers that stably grasp a set of objects and are geometrically compatible with all input objects. To accomplish this, we use an expressive shape parameterization and a tractable formulation. Thank you.